This particular lecture is going to discuss range animal nutrition, and in the past we've discussed plant morphology. Now we're going to focus on the inherent chemical properties of plants in the topic of range nutrition. This has implications on using animals as a tool to manage rangelands. So, a brief overview of this lecture. First, we're going to look at range nutrition and what it is, what it entails. Then we're going to look at the different classifications of nutrients. I want to talk about fiber and the property of fiber on animal intake. Then ultimately, I want to focus and touch on energy values of feedstuffs. There are two energy systems, TDN and NE. By the end of this lecture, you're going to know what both of those mean. And at the end, I'm going to sum it up. So the first slide, we're going to go into range nutrition. And ultimately, ranching manages animals, which can ultimately harvest the natural resource plants that converts solar energy into plant material. And ultimately, herbivores are going to harvest that plant material and convert it into a high-quality human food source. Now, grassland ecosystems produce plants that contain energy, and herbivores can access that energy because they have microorganisms that produce enzymes, chemicals that can break down plant cell wall components. So they produce enzymes, which ultimately the animal can get energy out of plants. So, what are the products and byproducts of plants out on the range? Well, products such as meat and milk are what we can benefit from as humans. We can consume the meat from animals that harvest this plant material. We can get milk. Some of the byproducts include the hide, the wool, and the manure. So products are what humans can consume, whereas the byproducts are materials or secondary products from those animals. Now, focusing on the classes of nutrients. There are 6 classes of nutrients that are required to maintain normal body structures, functions, and growth. Those are water, vitamins, minerals, carbohydrates, fats, and proteins. Now, these 6 nutrients are extremely important, so what I'm going to do is really focus on each of them one by one and give you a clear understanding of how important they are to animals. So the first nutrient that I'm going to focus on is water, which is the largest single component of the body. It makes up our blood, and it allows for the critical and optimal performance of the animal. It's important for serving as mediums for chemical reactions. It's necessary for digestion and for cellular metabolism. Water is also important for regulating body temperature. And some of the common sources of water includes wells, streams, farm ponds, reservoirs, and plants. So the amount of water consumption varies depending on animals. For example, a 1,000-pound non-lactating cow can consume about 9 to 12 gallons of water per day, and that's if it's 50 degrees Fahrenheit. Sheep and goats consume about half a gallon and 1.5 gallons of water per day. And looking at some wildlife species, pronghorn antelope consume about a gallon per day, but it really depends on the amount of water that these pronghorn antelope can access in plant material as well. So water is extremely important, and it needs to be made available to the animal. It needs to be clear, clean, and accessible. Now, water requirements are affected by temperature. At lower temperature, animals are going to consume less water. As temperatures get hotter, they're going to require more water. Ultimately, water intake influences the amount of food intake, how much of food, plant material animals are taking in. So the less water that they're consuming, ultimately the less food that they're going to consume. And one of the strategies to distribute livestock among landscapes is to move water sources, because animals are going to stay near that water. So if it's possible to move water source, then animals will access parts of the landscape where they weren't grazing beforehand. The next nutrient that I'm going to highlight are the vitamins. And vitamins are organic compounds required in trace amounts in the diet for normal metabolism. Vitamins are structurally unrelated, and each vitamin has a specific function. So there are two classifications of vitamins. The first class are the fat-soluble vitamins. These are vitamins like A, D, K, and E. And these fat-soluble vitamins are ultimately stored in tissue, where the other vitamins, water-soluble vitamins, are not. And those include the B complex vitamins and also vitamin C. So focusing on the fat-soluble vitamins, vitamin A is necessary for reproduction and also for vision. It's present in green leafy plants, but destroyed when ultraviolet light hits the plant and decreases with plant maturity. So ultimately, when ruminants consume green leafy vegetables, they can actually store vitamin A in the liver. And it can be stored for 6 to 12 months. In mature animals, calves don't store it as long, but ultimately they have that vitamin A accessible to use it in times where the forage isn't green, so during the wintertime. Vitamin D is synthesized by the animal when ultraviolet rays hit the animal from the sun, and that's necessary for calcium absorption. Vitamin E is necessary for immunity, for the health of the animal, and ultimately to make sure that the cells function properly. And vitamin K has a role in blood clotting. So if there's a gash in the animal, ultimately it'll clot that wound. So vitamin A, K, and E are high in green leafy plants, but all of them decrease with maturity. So there's a range illness due to vitamin A deficiency after ruminants graze dormant grasses for over 120 days. And this is over 120 days of severe drought. And animals can actually be subjected to night blindness. So that's one of the possible negative effects of having a vitamin A deficiency, is that the animals can become vision impaired. Now, minerals. Minerals are solid inorganic crystalline elements which cannot be decomposed or synthesized by the body. Therefore, they have to be obtained through the diet. Minerals serve as catalysts in digestion and metabolism, and they're divided into two classes. The first class is the microminerals. They're present in the body at levels greater than 100 parts per million. And these minerals include magnesium, calcium, phosphorus, sodium, chloride, potassium, and sulfur. Now, I really want to focus on calcium and phosphorus. Calcium, as you know, is necessary for strong bones, growth, but phosphorus is just as important, if not more important. Phosphorus is necessary for energy. Without the phosphorus, the animal can't access or make energy necessary for normal bodily functions. So those two elements are typically shown, and animals have a specific calcium and phosphorus requirements. Now, the microminerals are present in the body at levels generally less than 1,000 parts per million. These elements include manganese, iron, copper, zinc, molybdenum, selenium, and fluoride. And so these are required at lower levels, and typically if the animal is not getting enough of the microminerals, they can become deficient. Production is going to go down, and what we're going to discuss in the future is how we can supplement these microminerals in the diet so the animal doesn't suffer from poor production. Carbohydrates. Carbohydrates are the main source of energy in livestock diets. They're molecules that are composed of carbon, hydrogen, and oxygen, and therefore commonly referred to as CHOs. So energy supplied by carbohydrates is used for maintenance, growth, reproduction, and production. So what is maintenance? Maintenance is the energy that's necessary to facilitate normal daily activities such as thermal regulation, which adjusting body temperature, respiration, breathing, growth, and reproduction. So it's the energy necessary for normal body growth. And typically it's measured as nitrogen-free extract. So nitrogen-free extract are the soluble sugars and starches, or the cell contents from plant material. And more nitrogen-free extract is in younger plants because they have more cell contents compared to mature plants that have more cell wall components. So the more mature that a plant is, the lower the NFE. The younger the plant, the higher the NFE. Fats. Fats are necessary for the absorption of fat-soluble vitamins. Once again, those are vitamin A, D, K, and E. And they serve as a cushion to protect vital organs, but they also contain 2.25 times more energy than proteins or carbohydrates. Fats from plant material can be quantified as ether extract. And this is important because seeds are a high source of fats compared to the rest of the plant material. And this can be extremely important because sage grouse will eat seeds during the wintertime when other plants are unavailable or are low in energy. They can really find the plant seeds and get the energy necessary to stay alert and alive and productive. Proteins. Proteins are organic compounds composed of carbon, hydrogen, oxygen, but unlike carbohydrates, proteins have about 16% nitrogen. Proteins are building block for muscles, tissues, and also necessary for proper cellular function. Now, in order to obtain a protein value from plant material, there's a chemical analysis by which the percent nitrogen can be obtained through a laboratory procedure. You get the percent nitrogen and you multiply that by 6.25 and you ultimately get the percent crude protein. So this is called crude protein because that percent nitrogen that's obtained through a laboratory analysis, that doesn't discern if that's nitrogen from protein source or non-protein source. So urea, for example, is supplemented in feed. Sometimes they'll inject urea into hay bales, but that has nitrogen in it, but that's not protein. So when you do a chemical analysis of a hay bale with urea injected into it, the percent nitrogen is going to be a lot higher, and that's going to give you it's a crude estimate of the protein in that bale of hay. So once again, crude protein isn't an exact measurement, but it's a good indicator of how much protein the plant material or the forage has. Now, protein is typically the most expensive nutrient. And just to give you a ballpark range, about 30% crude protein is pretty darn good. That's high. That's excellent. Now, on the other side of the range, it can be about 4% crude protein, and that's real poor. 4% crude protein can be oat straw, whereas 30% crude protein can be young, immature alfalfa. What do I want to say? So this illustration shows that protein in forages correlates with forage maturity. On the y-axis, I have relative percent crude protein, and on the x-axis, I have the different seasons of the year. And generally, the variation in crude protein changes with season and even from year to year. So forbs, and you can even put shrubs there as well, typically have higher crude protein concentrations compared to grasses. And forbs, or non-woody broadleaf plants, they can be typically considered as weeds, but are pretty palatable. That means they're tasty for the animals when they're immature. And examples that are high in protein and digestibility are plants such as gayfeather, western yarrow, prairie clover, and Indian paintbrush. And on dryland ranges, high dormancy alfalfa can make a very good supplement for livestock, as do bird's foot trefoil, which in addition to being high quality forage, have an anti-bloat characteristic as well, meaning that the ruminants that consume this aren't going to have a buildup of gas in the rumen that they can't expel. And as we discussed in the last lecture, briefly, bloat can be fatal to animals, and that's when they eat young, mature legumes. So now look at grasses. Grasses are divided into two types, as Dr. Launchbow discussed. They're warm season and cool season grasses. And on semi-arid prairies and western ranges, warm season grasses do most of their growing from May to August, whereas cool season grasses do their growing from March to June. And you need to know which type of grasses are in your pastures to help you really determine when to graze and take advantage of the highest nutrient content. So in the spring, grasses will have protein content approaching about 20%. And that'll decrease as the plants begin to proceed to mid-bloom. And so that'll be about 10%. And when the plants develop a seed head, they're going to be less than that, so less than 10%. So weedy grasses can really be a good nutrient value, but generally don't produce enough annual forage to meet the needs of grazing livestock, and are often vegetative for a short period of time, as with cheatgrass and squirreltail. So ultimately, the nutrient composition, the protein, are going to change, and you need to determine what plants are on your piece of property or on the landscape, and what will they supply to your animals throughout the year. Fiber analysis is important to determine how much plant material our animals are going to consume. Neutral detergent fiber is commonly used in range nutrition. And what neutral detergent fiber is a laboratory procedure that's used to measure cell wall components of a feedstuff or of plants. And these three components are hemicellulose, cellulose, and lignin. Now, feeds with a high NDF contents are harder to digest compared to plants with lower NDF contents. And to kind of give you a range, about 40% NDF is excellent. It's plant material that's low in hemicellulose, cellulose, and lignin, whereas about 80% NDF is poor. That's going to be a range with, for example, oat straw. It's going to have a lot of fiber. And forbs and browse species have less or have a lower NDF compared to grass. So we focused on these 6 different nutrients. Now the question is how about energy? The next question is how about energy? Now, energy is derived from 3 of the 6 nutrients. It's derived from carbohydrates, fats, and protein. Now, what is energy? Now, energy is defined as the potential to do work and can be measured only in reference to defined standard conditions. Thus, all defined units are equally absolute. And that's what the National Resource Council defined as energy. But let's really go ahead and focus in and see what. There are 2 commonly used methods of measuring or expressing the energetic value of a feedstuff. The first method is total digestible nutrients, or TDN, and the second one is net energy. So the TDN energy system produces values for feeds that are calculated from estimates of the digestible chemical components of feed as follows. The percentage of total digestible nutrients equals, it's the percentage of digestible crude protein plus the percentage of digestible crude fiber plus the percentage of digestible NFE, or nitrogen-free extract, plus the percentage of the digestible ether extract times 2.25. So ultimately, TDN is a lab measurement of digestibility of a feed or plant sample, which is relative to its energetic value. So if we look on the right, you can see different feedstuffs and you see the percentage TDN. So alfalfa, fresh alfalfa has about 61% TDN, meaning if an animal consumes 10 pounds of feed of fresh alfalfa, they're going to be able to digest 61% of that 10 pounds, or 6.1 pounds. So TDN values are common on forage analysis reports, and TDN is not commonly used in ration formulation because it does not account for all the losses that can occur in fermentation and metabolism when forages are fed. So typically in range nutrition, you're going to see percent TDN. If you don't see percent TDN, you're going to see the second type of energy system that's used, and that's net energy system. The second energy system is the net energy system, and this is measured typically in millicalories per pound. How many calories per pound of animal is necessary? Or how many megacalories per pound of feed do we have out on the range? So a more specific measurement, this is a more specific measurement of energy, and the energetic value of feed differs depending on the function of energy it's used to power. So there's net energy for maintenance, and if you remember, maintenance is the caloric energy necessary for normal body functions, with minimal activity. There's net energy for growth. That's how much energy is necessary for growing or for adding weight. And then there's net energy for lactation. That's how much energy does plant material have that can be used for lactation in females. So energy intake is the number of calories that's consumed by an animal. So once an animal consumes plant material, it's taking in a certain amount of calories. Now, there are certain bodily processes where calories are going to be burned and not available to meet the animal's maintenance energy requirements. So, intake energy is the calories consumed. Now, the digestible energy is some of the calories, the energy that's left over after fecal energy is removed. Right? The animal's going to have to burn calories in order to make feces. Well, you take those calories away, and we have digestible energy. Now, from digestible energy, we have conversion to metabolizable energy. And ME is the amount of calories that's left over after the urinary energy and gaseous energy is subtracted. The animal requires calories in order to produce urine, and it requires calories or energy to produce gas. You take those calories away, and the amount of calories that the animal has to use later for metabolizable energy is a lot less. So ultimately, we get net energy, and you get metabolizable energy minus the heat energy, the caloric energy necessary for the animal to maintain body heat, or the heat necessary for fermentation to occur in the stomach, and ultimately you're left over with net energy. So you can see the gross number of calories in intake energy, and ultimately you get net energy. So calories are lost as food goes through the animal. And what we have in net energy is what's available for the animal to utilize for maintenance, growth, and lactation. In summary, there are 6 nutrients that are essential for normal maintenance, growth, and production. There's water, vitamins, minerals, carbohydrates, fats, and proteins. The nutritional composition of forage depends on the stage of plant maturity, and there's seasonal and also yearly variation. The percent total digestible nutrients is how much of a feed the animal is expected to digest and utilize. So TDN is commonly used in range nutrition. And the second type of energy system used is net energy, and that's utilizable energy from plant material. So the 2 energy systems commonly used are TDN and NE. And ultimately, the energy flow diagram demonstrates that the initial energy values of feed, for example, intake energy, ultimately produces net energy, which is the energy that the animal can utilize for maintenance, growth, and lactation. So I hope this provides you just a broad overview of range animal nutrition. And the next lecture is going to focus on animal demand. Depending on where the animal is, which animal, what breed it is, environmental factors, all these play in animal demand. And now that you know a little bit about range nutrition, we're going to focus on animal demand next.